So we're into chapter 8 on internal flow. And if you take a look at it, yeah, it's a long chapter. It's a very important chapter. But take a look at the first section of it, 8.1. It starts off with hydrodynamic considerations. We don't even get to anything thermal until section 8.2. So it's a big review of really the fluid mechanics. And that's really important because we're going to add a layer of complexity on top of it, okay? So let's talk about pipe flow. We have a pipe like this, and somebody says, I want you to tell me if it's a laminar flow or turbulent flow inside that pipe. How would you make that determination if it was going to be laminar flow or turbulent flow inside the pipe? How would you do it? You would calculate the Reynolds number, and the Reynolds number is defined for a pipe rho u d over mu. So we put a subscript d to say that's our length scale for the pipe. The diameter of the pipe is the length scale. It's the inside diameter that the fluid flow flows through. Okay. Little question here. Sometimes they'll put a little subscript m on that u sub m. What is that? It's a mean velocity. It's a mean speed. It's the average speed, because we know that the fluid flowing right next to the wall of the pipe, because of no slip boundary condition, it's really not flowing. You have to move a little bit away, but in the core, in the middle of the pipe, it's flowing the fastest. So near the walls, slow. In the core, fast. So the Reynolds number is also, we have an interpretation of the Reynolds number. It was interpreted as the ratio of some competing forces. It would be inertial to viscous. And so when it's high, the inertial forces win, and it makes it turbulent. That's the prediction of having turbulent flow. So the Reynolds number, based on diameter for critical, the transition between them for pipe flow is 2300. Now, some books will use 2100. Some books will just say 2000. This book, I believe, says 2300. So let's stay with 2300. But it's really not that accurate. It's in this vicinity where if you're below it, we would say you're going to be laminar. If you're above it, you're going to be turbulent flow inside the pipe. Well, we do have some entrance region to the pipe. Let me come back here and modify this illustration. So the pipe, there's some region at which there's flow, and it's starting to develop. So right at the inlet to the pipe, the flow may be very uniform. That's what we would expect. If it's coming from a pretty quiescent tank, it's not going to have a large velocity distribution. It's going to be uniform velocity over the entrance region to the pipe. And then the presence of the wall is felt, and just like we have a growth of a boundary layer, we're having the growth of the influence of the wall into the core. And after a while, down the length of the pipe, it becomes what we call fully developed. And if I sketch the velocity profile down here, if it was laminar, your memory may say that it looks very parabolic. It's a quadratic or parabolic. So this is the center line. And we measure R, the radius, going from 0 at the center line out to cap R, which is the radius of the pipe, the radial coordinate direction. And so here we would have U is a function of R, where at R equal to 0, it's the maximum. R equal to cap R is 0, some velocity profile. But if we come back to this location, we sketch the velocity profile. It's like the middle part hasn't felt the presence of the walls of the pipe yet. It's still developing. And yet, so we have a velocity profile that's flat in the middle and then like that. Okay. Again, this shape is if it's laminar fully developed flow. If it's turbulent fully developed flow, it's flatter in the core region. Okay. So what is that distance at which you become fully developed hydrodynamically? See, we're measuring x X is our distance measured from 0 at the entrance all the way down the length of the pipe. And so when X is greater than fully developed hydrodynamically, we would say it's fully developed flow. But what is our equation to have fully developed hydrodynamic flow? And there's really two cases, and it depends on whether or not the Reynolds number is less than 2300 or the Reynolds number is greater than 2300. Are you expecting turbulent flow? It'll develop typically faster, quicker. Okay, so the equation for the distance is 10 diameters. And that's one of the things you should never forget out of your fluids class, and I'm reminding you now because it's very important out of this class. If you go down 10 diameters in its turbulent flow, basically no matter what disturbance you had, it'll like entrance into the pipe or maybe going around the bend in the pipe or going through a valve in the piping network system, you will get back to being fully developed if it's turbulent flow in the pipe. And a lot of problems in engineering applications are turbulent. And so one of the classic things in a plant is where do you put the flow meter? And if the flow meter assumes that it's fully developed turbulent flow, where you put the flow meter, you look upstream of that flow meter and make sure you have 10 diameters. And I've seen cases where they don't. And then they have bias in the flow meter readings for the life of the plant, whenever it's running. And so take that away. This is one of the little things, hopefully, that you remember, because if you get out there and you have to work in the field with flow meters and whatever else, heat exchangers and other things, the technician will put a flow meter 2 diameters right away from some disruption. And it's like, right away, it's terrible. Okay, so there's a good equation to remember. 10 diameters, turbulent flow in a pipe, that's the length required to become, again, fully developed. Now, if it's laminar, the equation is a little more tricky. It's 1/20th of a diameter multiplied by the Reynolds number. And so you can explore this equation for laminar only, and you can say, well, what happens if the Reynolds number is 20, 200, or 2,000? Whoops, I messed that up. 20, 200, or 2,000. How many diameters do I need to go down to become fully developed hydrodynamic? Well, if it's your Reynolds number is 20, I mean a really low flow in a pipe, it's barely moving, right? You could just do it. You stick in the 20 there. The 20 over 20 cancels. It's 1 diameter. Okay, but let's put in a Reynolds number of 200. 200 over 20, that's 10 diameters. And if you put in a Reynolds number of 2,000, it's still laminar, but you're getting close to becoming turbulent. Then it's how many diameters? 100 diameters. So there's really, unfortunately, laminar flow, you have to pay attention. It's like, okay, be careful here. It really depends on what is your Reynolds number. Okay, let's press forward. So we mentioned that the velocity profile in the pipe, when it's fully developed hydrodynamically in its laminar flow, we expect a parabolic. How do you get that? So this is a review of the fluids. Well, you're going to have a quote-unquote a DE with 2 BCs. You know what that jargon is. You're going to get a differential equation. Differential equation which will have U as a function of R in it, and then 2 boundary conditions, and then you solve for U as a function of R. What would be our governing differential equation? Well, for a little chunk of fluid like this in there, they do a balance. Now, it's not accelerating or decelerating, so I don't have any change in the linear momentum flow rate in as or out of that control volume, that little control volume written right there. It's basically what flows in, flows out. So there's no change in the linear momentum flow rate. But there are things which tend to balance each other. You have viscous shear forces acting, as well as the normal pressure forces acting on that little control volume. And you derive the continuity equation in differential equation form, and it looks like the mu, that's our viscosity, divided by r, the location radial coordinate. You have the derivative with respect to r du dr. Again, r is that radial coordinate, u there is that x component of the velocity going down the direction of the pipe, and it's equal to dp dx. So I have pressure changing, and pressure is just as a function of x down the pipe. And our boundary conditions are very simple. We have that the derivative of u with respect to r at r equal to 0 at the center line is 0. And then the other one is u at r equal to cap r, no slip, is also 0. So we say that the 3 dots with the 4-letter word work. Like, hey, we've set up differential equations, separate, integrate twice, get those constants of integration nailed, and you get that the u is equal to r squared divided by 4 mu times dp dx. And what we'll do is tuck a negative sign with that dp dx, because if you think about it, is the pressure is high here and the pressure is low there. This is the direction of positive x. And so the pressure gradient is from high to low. It's like a negative slope. So we put a negative on there, so this term is by itself positive. And then we finish out this equation. It's 1 minus lowercase r over cap r squared. That's how you get the quadratic nature of it. Then you check the equation and it works. You also look at it and you say, well, what is the maximum? What is the maximum speed? Well, it's when lowercase r is 0 at the center line. So now we have an analytic expression for what is its maximum. It's equal to cap r squared divided by 4 mu times negative dp dx. So sometimes they'll just write u is equal to u max times 1 minus lowercase r over cap r squared. Quadratic, and it's a very simple expression. There's the details if you want to check it. So separate, integrate, use those boundary conditions. You can do it. Once we have u as a function of r, we can get the mean velocity. That was that um. That was the velocity needed in the Reynolds number. Okay, so how do I get the equation for the mean velocity? I like to think of it as doing this. Is you have a simple expression for the mass flow rate, and then you have a very accurate integration expression for the mass flow rate. So simple versus accurate. And the accurate is based on some integration. Okay, so what's the simple expression for the mass flow rate? Well, it's maybe like this. M dot's equal to m dot, and then you have simple, then you have accurate. So the simple would be the density of the fluid, the mean velocity of the fluid going down the pipe, that's that average velocity, times the cross-sectional area of the pipe. Wouldn't that give me a good expression for mass flow rate? And this is where I'm going to then get the definition or an expression for use of m. So if I look at my pipe, again, I'm sketching it here. If I turn it and look like this, and my velocity is only a function of r going from 0 to cap r, at any sort of little ring like this that has the same speed. A smaller ring, tighter into the middle, has a higher speed, and the ring that's further out has a slower speed. So what I'll do is I'm going to say I'm going to do an integration. It'll be this m dot is equal to the integral of a lot of little dm dots. And so what's the little flow rate in each of these little rings? So each little ring has a density, has a speed at that ring, and that little ring. And then it has the area of the ring, and that area of the ring would be the circumference or the length, the perimeter of that ring times dr. So that would be the 2 pi r dr. So this is the integral from 0 to cap r of rho u, I need that as a function of r, times 2 pi r dr. So now you can come in here, sometimes they'll cancel that, but it's really a mass flow rate. Now I'm kind of, what are we doing? A volumetric flow rate? If the mass density is constant, yeah, then you can express u sub m as a volumetric flow rate equation instead of a mass flow rate. And then we get u sub m is equal to 1 over a sub c, the cross-sectional area, integral of 0 to r of u, 2 pi r dr. Sometimes they'll forget and they'll just say, look, let's call this dA, the little area of the ring. The little area of the ring is 2 pi r dr. So different ways of expressing it. Let's say you put in here 1 over pi cap r squared, integral 0 to r, u, 2 pi r dr. It's even getting a little more abstract. You can cancel the pi's. You can move this r squared inside, put it over cap r, put it over cap r. And then we had a change of variable, so now it's the integral. U is a function of some new variable times 2 times r hat dr hat, and r hat goes from 0 to 1. Okay, so there's a couple different expressions for it. Maybe the best one, maybe I should have written it like this, is dA. This is a very good expression for the mean velocity, right? Hey, Professor, we just solved for u for the analytic solution. It's a quadratic. Hey, we can now do that, right? So if we come in here and we say, hey, if our laminar fully developed flow, u is equal to u max times 1 minus r hat squared. And then you just look at it and you say, for that laminar fully developed, the mean is equal to, you just do this integration, and you're going to have the 2 can come outside. You have the integral from 0 to 1 of r hat times 1 minus r hat squared dr hat. And that's going to give you, I forgot the max, u max, 2u max. Anyway, if you've done this a few times or at least once in your life, what do you find that this mean velocity is compared to u max? We're fully developed laminar flow. 1/2. It's 1/2. You can fill in the details right here, a couple dots with a little WORK, and it's simply integration. All right? All right, let's press forward. Oh, there's the details if you want to follow them. You know. All right. All right, now we want to talk about that pressure gradient and the wall shear stress. So I have the flow in this pipe, and what I do is I focus on, you can call it a control volume for fluid mechanics background, or you can call it a FBD if you really like or excelled in statics. It's the same thing. What we have is just focusing on the fluid, we pull this out and we focus on it right here. And we say we don't have any change in the linear momentum flow rate of the fluid that's coming in on this side and going out on that side. It is the same, it's fully developed. It doesn't matter if it's turbulent or laminar. It's fully developed. The linear momentum flow rate's not changing. It's not accelerating or decelerating. The diameter of my pipe is not increasing or decreasing. All right. So I have a force per unit area acting on the inside inlet and a force per unit area acting on the outlet. What do you mean, force per unit area? Yeah, it's the pressure at this location X, and it's the pressure at X plus delta X. And the first time you take fluid mechanics or you're taking fluid mechanics, you say, Professor, I think you've drawn the arrows on the pressure on the outlet in the wrong direction. Shouldn't they be in the positive X direction, just like on the pressure at location X? And that's not true. That's right. You go back to hydrostatics and the concept of pressure. And if my focus is on this control volume, the pressure is always pushing in to the middle, inside. So that's the correct direction. And then you think, well, if the fluid flow is going that way, then what about the wall shear stress? What's happening at the wall? Well, we're having this symbol like this, tau, at the wall. Isn't that a force per unit area, shear stress, acting on the wall? So what do we have? Two things in our force balance. We have the pressure at X times A sub C. What do you think A sub C is? Cross-sectional area, pi d squared over 4, or pi r squared if you like working in radius. That's pushing it in the positive X. In the negative X direction, you have pressure at X plus delta X. This little chunk is length delta X times the same A sub C, plus pushing back in that same direction is the wall shear stress. Now what is that multiplied by? Is that multiplied by A sub C times delta X? No. So what's it multiplied by? Something times delta X, but not A sub C times delta X. I need the area, pi d. Pi d, that gives me that perimeter, pi d times delta X. True? Very good. So at this point, you can flip this one over to the other side, and what you'll get is you'll get negative P at X plus delta X minus P at X times the cross-sectional area. I'm going to put pi d squared over 4 is equal to the wall shear stress pi d delta X. What do you think we're going to do with that delta X? Bring it over underneath the delta P, and then they always put a little LIM as delta X goes to 0. Aren't you glad you took calculus? Spent all that time trying to figure out what a derivative is. And here we just reestablished what a derivative is. So this derivative, you get negative dp dx is equal to, we can now cancel maybe this pi, cancel one of the d's. It's equal to the wall shear stress times 4 over diameter. Did I do the math okay? Does it look okay? Good. Well, what was our definition of friction coefficient C sub F coming from a flat plate? Our definition of the friction coefficient was the shear stress divided by 1/2 rho u infinity squared. What we're going to do now is I'm going to say for my flow inside of a pipe, I can still have this concept of friction coefficient. It's a normalized shear stress. Let me put d over 4. I'm going to leave the 1/2 rho u mean squared. And we replace tau with negative dp dx. C sub F, the friction coefficient for now flow inside of a pipe, okay, is equal to this expression. I eliminated the tau using this expression right here, right? If you look at this for a minute, you say, this term right there is very familiar. That term is my lowercase f, my friction factor for flow in a pipe. The friction factor is negative dp dx times d divided by 1/2 rho u mean squared. And so this brings one of the more confusing areas of fluid mechanics and heat transfer. Sometimes you'll see people, when they're talking about flow in pipe, they'll use this friction coefficient. And if you look in the history books, they'll call this the fanning, F-A-N-N-I-N-G, fanning friction coefficient. Or they'll use the friction factor, sometimes called the Darcy Friction factor, sometimes called the Darcy, I'm going to butcher the name, Wiesbach friction factor. So sometimes they'll have a D or a DW subscript on it. And the big difference is the C sub F is equal to the 1/4 the friction factor. Okay. With that, you go to the Moody diagram. When I teach fluids, I'll even tell students, I'll say, okay, I'm going to tell you one of the problems on the final exam or third exam or whatever exam it is, and it's going to be like 10 points worth of exam. And it'll be the first part of the exam, it'll be a blank sheet of paper, and I'm just going to give it to you, and I'm going to say, from memory, no notes, no nothing, reproduce as accurately as possible with all the detail as possible, the Moody diagram. And I think you should, if you want to work in this field. Now, if you're a stress-strained person or a mechanics guy, whatever, you never want to work in thermal fluid, you never want to see another pipe or a pump or a heat exchanger or power plant or anything like that, fine. But if you want to work in this area, this is a good thing to sort of get deep into your mind. I don't know if, I tell you what, I've always been impressed. When I tell them what's on the exam, the students come prepared. And I'm telling you, some students have given me excellent renditions from their memory, no notes, no nothing, to scale the Moody diagram. Oh, it's impressive. This is easy. This is easy when you look at it. Let's take time now. Take a look at the Moody diagram. What's on the x-axis? Oh, and if they didn't label the x-axis and put how they calculate the Reynolds number, they lose some points. And I tell them that before the exam, so they know they've got to put everything down. What is the minimum value? What's the maximum value? Is it a linear scale or a log scale? Log, and there are a lot of decades. Lots of orders of magnitude, I should say, not decades, on here. So it goes from, what's the lower value right there? About 1,000. Some of them will go lower than, but this is like maybe a couple hundred. And then this is 10 to the 4, etc. Where's our transition between laminar and turbulent? Around 2,000, right? Around 2,000. Most of the Moody diagrams dedicated to turbulent flow. Some of it's dedicated to laminar flow. What's on the y-axis? Hey, that's what we just talked about, our friction factor. Hey, do you like that equation? Is that the friction factor, the equation for it? Negative dp dx with the negative sign there. D, then 1/2 rho u m squared. Some books will write it a little differently, but that's a good way of remembering it. Okay, y-axis. Linear or log? Linear scale or log? Professor, I came here, I paid my tuition. You tell me. It's like when I go to a movie theater, I don't talk on my phone, and I don't talk to my neighbor. I just sort of veg out and enjoy the movie. I'm ready to enjoy a movie. These are comfy chairs. What is it? It's log scale. Now, sometimes it takes students a while because it's rare that you see a log scale and they only have basically one factor of 10. Look at the x-axis. It goes factor of 10, a factor of 10, a factor of 10, a factor of 10. They have a lot of orders of magnitude. Here's just one. I know there's a little bit down here, but primarily one. But the way you can definitely tell is if I'm moving from 0.01 to 0.02, what is that change? That was a change of adding 0.01. Let's go up to 0.09 and add 0.01. Where will we get to? We'll get to 0.1. So this is the same magnitude of addition, change in the y, 0.01, as this. And those are not the same lengths of the line on the y-axis. So it's definitely a log scale. Now, also, if you really pay attention to the numbers, sometimes students or other people will make some calculations. Hey, yeah, the friction factor came in to be 42.9. Excuse me? What's your definition of friction factor? Is it consistent with what this is? And if it is, go look for your error. And that's very valuable in engineering. It's like, are you in the right ballpark, or are we looking at an error somewhere in your calculation? Somebody else, oh no, my friction factor is 10 to the minus 8th. Really? Okay. Let's explore that a little bit, because it should be roughly between 0.01 and 0.1. Now, yeah, you can extrapolate a little bit beyond, but most of it is, that's the action where it's happening. Got it? All right, so what's this red line doing over here? It's in the laminar flow region, and we have the friction factor given by a simple expression of 64 over the Reynolds number. On a log-log plot, it's a straight line. Otherwise, it's not a straight line on a linear plot. Do they have multiple curves over here in laminar, or just one curve, and it's 64 over Reynolds number? Just one curve. All right, let's take a look. The majority of it is out here in the turbulent flow regime. Why do they have all of these curves? What's the difference between that one, this curve? What are the difference in all these curves? The relative roughness. So over here, this is a line right here with the relative roughness, 0.05. Here's a line, relative roughness, 0.000, whatever, 2, if I read that correctly. Here's one with a very small relative roughness. So what is this epsilon over D? What is that epsilon? Well, think about the wall of the pipe, and it's some roughness measurement. So if I have a concrete pipe, your experience with concrete, not that smooth. If I have a steel pipe, a little smoother. If I have a copper tube, drawn copper tubing, hopefully you have some experience with things like that, or plastic pipe, it's very smooth. So down here, they'll have a little scale. Hey, if they left off that little box, lose a point. Anyway, I had people come in with very accurate, because I told them what I was looking for. And that was the first 10 minutes of the exam. Here it is. And they were able to reproduce it. And yes, they put in there that, oh, drawn tubing, look at the value of that. It's very small, roughness. So copper tube, drawn tubing, or that PVC, very smooth pipe. But then if you come out here, concrete or cast iron, you have a larger roughness. Okay, so that's why you have so many curves. Professor, what is this dashed line doing? See the dashed line? What's it doing? It's separating two regions in the turbulent region. They're both of these subparts of the turbulent region. One is above the dashed line, one is below the dashed line. There's no dashed line in the laminar. Okay, so they call this one the fully rough zone. And they call this one the transition zone. I don't like those names. It's more the concept that I want to emphasize. Sometimes instead of being fully rough, I've seen fully turbulent. I think that's even more confusing. But fully rough doesn't make much sense to me either. I haven't seen great names for these zones, but I know what they're doing. So what's the deal with the fully rough zone? What's the observation that you can make about the red lines, the curves in the fully rough zone? They're all flat. They're all horizontal. For a particular roughness, for this roughness right here, it's flat, isn't it? For this roughness right here, it's flat. But when you get into the transition zone, it's curved. So this brings out my only clicker question for today. In the fully rough zone, for a given relative roughness, the friction factor is a constant, or increases with increasing Reynolds number, or decreases with increasing Reynolds number. All right, let's take a look at it. You know, you could talk to your friends. So you do have friends in this class. So, oh, they're competitive friends. So when they talk to you, you give them the wrong answer. Select D. Yeah, go for D. So it's a constant. Basically, what's interesting is if you have that roughness and you know it's turbulent out in this region, that you could slow the flow down or speed the flow up. Does the friction factor change? The friction factor is constant. It depends only on the relative roughness out in the fully turbulent zone. But in this region, the friction factor is a function of both the Reynolds number as well as the relative roughness. Okay. And if I'm in this region, if the Reynolds number goes up, what does the friction factor tend to do? Down, down, down. Okay. Let's jump back to the Moody diagram. Now, there's another section. If you have really low relative roughness, I know it keeps going low and low, low, you can get what they call a smooth pipe. And so this is the curve, the bottom of this is the curve for where you have smooth pipes. And in engineering, we have a lot of smooth pipe applications. And so even though this covers a large domain, often we're working with pretty smooth pipe at modest Reynolds number. At modest Reynolds number. So don't get too psyched out about this chart. A lot of times we have pretty smooth tubes or pretty smooth pipes, and we have modest Reynolds numbers in that vicinity. Okay. So that y-axis was the friction factor. The friction factor is defined as minus dp dx times the diameter divided by 1/2 rho u mean squared. If you wanted to calculate the pressure loss in a pipe, it would be equal to the friction factor times the length of the pipe compared to the diameter of the pipe times 1/2 rho u mean squared. You unravel it. This is the way I usually remember it. This one I have to think a little bit about. But this, if I wanted to calculate the pressure loss at a pipe, give me this friction factor, give me the length of the pipe, tell me the diameter of the pipe, tell me the speed and the fluid flow, and there you go. This is the velocity pressure, and there you go. This is a very useful, quick to use equation, use it a lot. All right. And like we were just saying, in some cases, if it's fully turbulent, this is just a constant. It's not a function of the Reynolds number. Okay. Well, how did we get that the friction factor is equal to 64 over the Reynolds number? Okay, go back to ME 3663. It's easy to show. In the interest of time, I encourage you to go back and do it. This is all a review of fluids so far. Let's try to get to some heat transfer. But it's worth doing and knowing that result. We already talked about the different fanning friction factor versus the Moody diagram friction factor. A few people call it that, but most of them will call it the Darcy friction factor. All right. So I have a pump. And the pump is driven by a shaft. So the shaft provides power to the pump. It's a rotating shaft. The shaft power comes from a motor. So we have the pump, we have the shaft, and we have the motor. This is one of those things where please don't leave this class or any engineering program without this knowledge. Okay, so we're having a flow of energy. We have the electric power coming into the motor. The motor converts that electric power into the shaft power. Some flow like kilowatts or horsepower, a flow of the rate of the energy transfer in that rotating shaft to the pump. And then the pump brings in fluid and spits out fluid. The pump brings in fluid at a pressure low, and it spits out fluid at a pressure high. Does the pump change the flow rate of the fluid through the pump? Does the mass flow rate of the fluid change? Only the pressure changes. So somehow we're getting power into the flowing fluid. And so there's three equations. The easiest one is somebody says, what tell me how you calculate the electric power that's supplied to the motor. If I knew the voltage, oh, it's 110, 480 volts, whatever it is. I also need to know whether it's single phase or three phase, and I need to know the power factor. But let's ignore those complications and just say the most fundamental is if I know the voltage, and what else do I need to know? Because I multiply it by the current. Then I can get a very simple calculation. Again, if you got three phase, there's a factor in there, and if you have a power factor shift, because it's induction, it's not all resistive, then you have another factor in there. Okay, but this is a good equation to remember. How about shaft? Somebody says, what is the power of a rotating shaft? It's a product of two things. This is the EE class that you took. This is the dynamics class that you took. A little review. What is the two things that are the product? It's the torque in the shaft. If it's got no torque from one end to the other end, it's not transmitting any power. It's got that rotational torque, okay? Times the rotational speed. All right. Then for fluids, for the fluids class, we say, what is the power that gets into the fluid? Well, it's a product. See the pattern? Engineering has lots of patterns. This is a good pattern. It's a product of two things. What's the pump really doing? It's like the torque was different on one end and the other end. Just like if on an electric motor, you basically have a high current and low current, or not current, high voltage line, and then basically a ground line. You don't want to guess which one and touch it, but it's like this line is 120 volts, this is 0 volts. There's a voltage drop across it. It's like there's a torque difference between the ends of the shaft. Here, it's a pressure difference. It's the delta P gain. It's the gain in pressure times something. What is it times? Flow rate, the flow rate through, just like the current flow rate. So it's a volumetric flow rate. So I encourage you to go back and review your fluid mechanics on that, because sometimes we're interested in how much of that energy gets dissipated from you always have an efficiency. So if the shaft power is coming in and you're supplying 900 watts or something like that, and the fluid power is going out 890 watts, where's the 10 watts going? Heating up the fluid. Or it's going into the room, heating up the air in the room. All right. We covered that. And I mentioned also that a lot of people have focused on the application of smooth pipes at modest Reynolds numbers. Here's a correlation. It's called the Blasius correlation. It's very old. And basically they said, you know, it's around 0.316 times the Reynolds to the negative 0.25. That's a curve fit right in here for smooth curve. It's try to stay less than a Reynolds number of 10 to the 5th. And it's not good to 10 to the 6 or 10 to the 7. What do you think we can do with that? We're going to use that with our modified analogy, Reynolds analogy between momentum, because this is what's happening, is you're having a pressure drop. It's related to the momentum, viscous effects, and so we can then get a heat transfer. So the Reynolds, modified Reynolds analogy will be used with a simple correlation like this to get a Nusselt number as a function of the Reynolds and Prandtl. What was our thing? It was C sub F over 2 times the Reynolds times the Prandtl to the third. That's our modified Reynolds. So you say, well, this is my friction factor, but the friction factor divided by 4 is C sub F, true? So basically, if I do C sub F over 2, that's friction factor over 8. And so what you'll get is quickly a Nusselt number is equal to 0.316 divided by 8. Then I have Reynolds to the negative 25 times Reynolds to the positive 1, Reynolds to the 0.75, Prandtl to the 1/3. Yep. And it works. It's old. There's more accurate or other correlations which are more popular. Well, with that, we've gotten a review of the hydrodynamics, and that was simple compared to the thermal considerations that we need to start now, okay? So let's do that. So let's take a look at some of our thermal considerations. Well, we're going to talk about the mean temperature, T subscript M. Was there a concept of a mean velocity? And they're very, very similar. So if you've got the concept of the mean velocity down, then it looks like, sure, that makes sense to me, the mean temperature calculations. We're going to talk about getting Newton's law of cooling. That'll be related to what's happening at the surface. We'll talk about fully developed flow. We'll have entrance regions, just like hydrodynamic and thermal entrance regions. Let's jump into it. So we have this circular flow, circular tube. Now, you can pick your concept. Do you want to run with the hot wall and a cool fluid? I think it's better just to pick one. And let's pick this one. So we have a hot wall and a cool fluid. We're going to have the concept that we need a certain length, because maybe this is where it enters from a tank, that it'll be fully developed thermally. Well, once it's fully developed thermally, let's go out here at this location right here and think about sketching the temperature profile. We sketched the velocity profile before. So if we have a hot wall, what we'll do is we'll put it this direction as a magnitude of the temperature. We'll call this TS, surface temperature. And likewise down here, TS. But the fluid is cool, so the temperature profile is kind of funny, isn't it? It's cooler in the core. All right, let me do this. Let me sketch that pipe going down further. And let's say that the temperature of the wall didn't change. So I'm going to try and make the length of this line right here, indicating the temperature of the surface, to not have changed, right? Okay. So that's my starting point of sketching the profile. But if this was my profile at this location, if I go further down the wall, should the profile be something more like this or something like that? Or should it be the same? Here's the clicker question. Should it be more like A, B, exact duplication of the one that it was a few meters before, or C? So, very good. Most students, that's a difficult concept. If you get that concept down, I think you're much better prepared for the difficulties that we're about to embark on for this problem. Because what's happening here is you're heating up the fluid. And so the whole fluid, sort of the average temperature of the fluid, the mean temperature has to go up, and C represents a higher mean temperature of the fluid. And where the velocity profile, once it was fully developed, did the velocity profile change? No. Temperature and heat transfer is much more difficult. Well, what do you think we get for the fully developed thermally equation? Well, we're going to have two cases. Basically, is the flow going to stay laminar? Is the Reynolds number below 2300? Or is it going to be turbulent? One is going to be easy. One is going to be a little harder for the equation. But what do you think is the easy? What do you think that distance to become fully developed thermally is for the turbulent case? What's the mechanism to transfer momentum? What's the mechanism to transfer heat, internal energy, and mix it up within a turbulent flow? It's the same little bulk motion mixing. So guess what? It's 10D. It's the same. This is the same as the hydrodynamic entrance length. Now, for the laminar case, we have the X fully developed hydrodynamic, and we scale it by the Prandtl number. So if you want to write it out, it's 1/20th times diameter times Reynolds number, but now we have a multiplier of the Prandtl number. So this one is, a lot of engineering applications have turbulent flow inside of tubes and pipes. When you have laminar, slow down, think about it, especially if you have an entrance region. Okay. Well, what about this mean temperature? I like to think of it as a simple expression and make that equivalent to a very accurate expression used involving integration. What do you mean? Well, I have some energy flow rate. Remember last time for the mean velocity we had mass flow rate? I need some simple expression for the flow rate of internal energy. So a simple expression for the flow rate of internal energy would be the mass flow rate times the specific heat of the fluid times the temperature of the fluid. The mean temperature of the fluid, the appropriate average mean temperature of the fluid. And so what about the more accurate involving integration? Well, I take my pipe and I look at it this way, and I have little rings of higher velocity pipe down the core. I'll go out a further ring and then another ring. So I'm going to do an integration, a summation over those rings. So it'll be the integration of the specific heat and the temperature in that ring times that mass flow rate in that ring. I'll sum up over the little mass flow rates for each of the rings. Let me write it this way. Rho from the m dot, this, and then the C, then the U, then the T, and then we're going to have the little dA. So the little chunk of flow rate will be rho U dA. Okay, so we have m dot, that mass flow rate we can expand rho, U mean, cross-sectional area, specific heat, T mean. I think if you got this equation down and you don't make any blunders, then you can work it out. Often they say, hey, we're interested in incompressible substances, constant density. Specific heat's not changing. So what we have is the equation for the mean temperature, 1 over U mean, cross-sectional area integral of U, which is a function of location, R, T, which is a function of location, R, and then the area, which is a function of location, R, dA, is that 2 pi R dr. There you go. That's how you calculate the mean temperature. I need to know the velocity profile as well as the temperature profile. But don't let this complex equation make it harder in concept than what you might think. Think about this. I have a pipe. If I could, for 1 second, divert everything flowing into that pipe into a well-insulated bucket, let that fluid mix, let it sit, and then measure the temperature of that fluid, it would be the same temperature. It would be that mean temperature. So sometimes they call this the mixing cup temperature or the bulk temperature, but it's the mean temperature. Again, take the thought experiment and for 1 second or 1 minute or whatever, some unit of time, divert all the flow at some cross-section in the pipe into a well-insulated container. Let it sit, let it mix, get one average temperature for that mixture, and there you go. Because some of the fluid is flowing in the center of the pipe, isn't it? And it's fastest. But I don't know the temperature there, but it's the average. And so if you said this was an average, it's a volumetric flow rate averaged temperature or a mass flow rate averaged temperature or even an energy flow rate average temperature. Okay, that's our mean temperature. So we have fully developed pipe flow with constant surface heat flux. So here is the entrance to a pipe, And I'm going to say at this location, it's fully developed both hydrodynamically and thermally. Okay. Maybe it's easier to think about turbulent flow in the beginning because they have the same entrance length. Okay. So if I have a constant surface heat flux, what does that mean? That means that Q double prime at the surface is constant. How would I achieve that experimentally? Take an electric resistive wire and wrap it at equivalent spacing going down, don't change the wrapping density, around the pipe. Insulate it very well, and then turn on electric resistive power to that resistive electric wire, and it'll heat it up like that. So that's how you experimentally you could achieve it. Now, what I want to do is I want to talk about as a function of location x going down, I want to talk about three things. I want to talk about the mean temperature of the fluid. Then I want to also talk about the convection coefficient. And then I want to talk about the surface temperature of the pipe. For those three things. Let's do them in that order. So for the first plot, we're going to plot the temperature, and I want to only consider when it's fully developed. Okay? Let's say the temperature was this amount coming in at that fully developed. What will the temperature profile look like from this point on? Will it be flat? Will it be a straight line up? Will it have some sort of exponential shape? Will it be a straight line down? Will it have an exponential shape? What will it be? What will that mean temperature? And so why is it a straight line up? No idea. Energy balance. Do an energy balance. Always go back to your energy balances. And so if I'm going this distance down, well, it's the Q double prime times the perimeter times that length going down. Maybe I call it delta X or L. And then it's the same amount that's into the fluid. And so if I come down here, another delta X, same additional amount's been added. The mean temperature is going to go up at a steady rate. Okay. Now, it's fully developed. Let's go down here and plot the convection coefficient. Who would like to try the convection coefficient? What's the convection coefficient? Let's say the convection coefficient's this amount. Should it be straight? Should it be going up? Should it be going down? Flat. It's flat, straight. What's the key? Why? Because it's fully developed. It's fully developed flow. It has the same convection coefficient. So now the last one, what is the surface temperature doing? We'll go back to this temperature plot, and we'll do the surface temperature. Let's say the surface temperature at this point is, 5 degrees higher than the mean fluid temperature at that point. Does it stay 5 degrees higher? Does it go flat and become somehow colder? No, come on. Does it go exponentially down? Does it go exponentially up? Well, the key is the H is constant. And you have that the Q double prime is equal to a constant H times T surface minus Tm. This is going up linearly. This is constant. That has to go up linearly at the same temperature difference. So this is Ts, this is Tm, this is H. Congratulations. Now, do you really want a challenging thought experiment? Let's do in the entrance region. And in the entrance region, what do we remember even from our flat plate? From our flat plate analysis, what was H as a function of X going from 0 out in our flat plate? Was it constant? Was it like this? Was it like that? What did H do? Close to the leading edge, this is the leading edge at 0. What was H? Really, really big? Or kind of average or really, really small? H, the convection coefficient, leading edge of a flat plate, knife-edged. Professor, I'd like to leave this classroom at this moment. I think I may have that discussed some more somewhere else. So if you, no, that's not where I want to talk about it. Not where I want to talk about it. Okay, well anyway, it's like this. It's very high. It goes off to infinity. There's a little singularity at that front, the leading edge. So if H is going off like this, okay, and I should have stayed with Tm. What is Tm doing? What's the bulk fluid temperature Tm doing? Back in this region. Is it straight back? Is it like this or like that? Do energy balance. Consider an energy balance. Just like this section right here, do this section energy balance, this section energy balance, this section energy balance. Is the flux the same? It's the same flux. Same amount coming in. So it's a flat, straight line. Just not flat and like horizontal, but it's the same slope. So that's what Tm is. H is going up, so what do you think Ts is doing? Kind of going down, or staying the same, or going up? These are tough questions, I know. But look, it's like this over here. The temperature difference driving that flux, this went way up. I need a smaller delta T to drive the same flux. So the delta T goes down. And actually, if H goes to infinity, these will come and pinch at x equal to 0. But that's a singularity. Well, we have what? How many minutes left? 9 minutes. That's a lot of time. We can cover a lot more material, huh? Professor, just tell me what's on the final exam and I'll be happy. Okay, no. Okay. What happens if you have not a constant surface heat flux, but what happens if you have a constant surface temperature? Same thing. We're going to have a pipe. All right. We're going to have an inlet to the pipe. We're going to come down here. We'll do fully developed thermally as well as hydrodynamically. I'm interested in the temperature as a function of location down, as well as H, convection coefficient, as a function down. Okay, this whole thing has the same temperature. So it's probably better to plot the surface temperature as the first one, easiest one to plot. That would be flat line, and no matter if it's fully developed or not. Got it? Now, let's say that we have a fluid, and the fluid is right there. It has some temperature right here. Okay, it's colder than the surface temperature of the wall of the pipe. What is it going to do? Stay down here? It's going to go up. Go up linearly, maybe even cross? No, never going to cross. Going to go up one of our favorite equations. What do you think that shape of that equation is? Exponential. That's right. I know that you have a new favorite called the hyperbolic tangent. I know you have a new favorite known as the error function. But don't forget your other old favorite, exponential shape. And it's going to, as you go down, 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 further, 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 Tm is going to get closer and closer to Ts. It can't get any higher than Ts. Now, what about the convection coefficient? Fully developed? It's just convection coefficient. You know what? The convection coefficient has the same profile as before. It really doesn't depend on that, the boundary condition. Okay, so we did the surface, then we did the mean bulk temperature, convection coefficient for the whole thing. Now let's go back. And we already did the surface temperature in the developing region. This is where it's developing. What about the mean fluid temperature in the developing region? Well, because this is higher, it's not a... This is a simple exponential because we have h is constant. This is never even a simple exponential anymore. But it's I don't know if I sketch it that well. It's not flat. I didn't put it close enough up. It's like a steeper, then it hits here, and then it's an exponential. Because for the same delta T, that higher H lets it heat up more rapidly. So it's going to be having a greater slope on the entrance region. Well, now you're ready, once you get a qualitative sense for it, to dive into the equations. We'll do that next time. Thank you for your attention. I'll be in my office if you have any questions.